Hey guys, it's me Active Exploit back again with a new video. And in today's video, I actually wanted to announce that I'm going to start a new series. And this series is actually all about exploiting stack-based buffer overflows, right? Now, I won't be explaining what exactly it is. So if you don't know what exactly are buffer overflows, you can just Google them, or you can just watch some tutorial videos on YouTube. And one of the best one which I found till now is by the Cyber Mentor. He actually did a great job at creating a series on stack-based Windows buffer overflows, right? So I only will be guiding you through the process of fuzzing and programming the exploit for the vulnerable program, right? So first of all, what lab setup do I have? So I got my Kali Linux machine over here, and I have my Windows 10 machine over here. I know that the screen is a bit small, and I'm sorry for that, but it is still visible, right? And the program which we are going to exploit in today's video is going to be a FTP server, right? Which is known as free float FTP server. So free float FTP server is a FTP server application which is basically for Windows, right? And if you just go on exploit DB and search for it, you'll find tons of exploit for that, right? So with that being said, let's get started. So first of all, let me actually describe the steps which we are going to use in order to exploit a buffer overflow vulnerability on Windows, right? So first of all, we actually start out by finding a vulnerable entry point in the program, right? Once we identify the vulnerable entry point, we start fuzzing that particular entry point, right? So in the fuzzing process, we basically try to crash the program, right? And after we verify the crash, we send a particular payload um, to the program so that we can find the EIP offset, right? So once we actually find the EIP offset, we are simply going to uh, control. We actually have to check whether we can override the EIP, right? So we basically try to control the EIP, right? And once we complete that step, then we move on to finding bad characters in the program, right? So bad characters, of course, we have to find them because if we don't find them, they actually might, um, you know, just mess up our shellcode, right? So after finding the bad characters, we finally move on to finding the Jmp Esp Pointer in the program, right? So it's basically we are going to jump our shellcode to the stack and execute it, right? And finally, after finding a Jmp Esp Pointer, we actually move on to generate the shellcode, right? So we basically generate our shellcode, and we also ignore the bad characters which we actually discovered in the process, right? So with that being said, the immunity debugger, I'm actually going to use immunity debugger for fuzzing process, right? So I can just open it, and let me actually make this a bit clean. So let me just get this up over here, this here, and this here. Alright, so now I'm simply going to open up my FTP server. So as you can see, I have the free float FTP server over here. Now, if you don't have the binary of this particular FTP server, I'll just include the link in the description, right? So you can just download it from there and start following the practical with me. So I'm just going to click on open, and I'm just going to click on run, and there we go. So our FTP server is finally running, right? And we can confirm that. Yep, there we go. So now let's just move back to our Kali machine, and let's just go to a terminal, right? Now let's actually try connecting to that particular FTP server, right? And as you can see, we get the banner. It says free float FTP server. So let's actually run some commands. Help. It says no help available. Alright, so now let's actually get started off by the fuzzing process, right? So I'm just going to open up a text editor over here, and I can just, whoops, I just want to increase the font if I can. Alright, there we go. So I'm just going to save this file over here in the free float FTP server directory. I'm just going to call this fuzzer.py. Alright, so now let's actually start fuzzing the program, right? So now we are going to use a module called socket in Python, right? So socket module can actually be used to create TCP and UDP sockets, right? So we will start out by importing the socket module. So we are just going to type import socket, and then we will be importing time. We also need the sys module, so import sys, and you'll actually come to know why do we need these two modules, right? So now we finally declare a variable called buffer, and we're just going to assign a value of assign 100 A's to it, right? And now we are basically going to enter in a while loop, so while true, and we'll be creating a try and except statement, right? So try, and we're just going to now create a TCP socket, right? So let's say s equals to socket dot af underscore inet socket dot sock underscore stream. So this command is basically going to create a TCP socket, right? And now we will just simply connect to our FTP server. So it's running on 192.168.1.34. So the Windows box of mine, it's actually sitting at 192.168.1.34, and we will be connecting on port 21, right? Alright, so now if you noticed, if we go back and once again connect to the FTP server, as you can see, once we connect to the FTP server, it actually sends us a banner. So instead of sending this buffer first, we will actually have to receive the banner, right? So we are simply going to receive for 1024 bytes, right? So now we finally will be sending user. So we actually need to be authenticated, and any username and password will work in this case, right? So let's say user anonymous, and we are just going to send this as a new line character, and once again we'll just receive 1024 bytes, and then we will finally send the password, which is pass anonymous, and once again we will be receiving for 1024 bytes, and finally we send our buffer, right? So we're just going to say buffer plus our new line character, right? And once again we'll just receive 1024 bytes, and finally we'll just send the quit command, right? To basically close the connection. Then we can just say s dot close, and we are just going to print out a statement so that we know the length of the buffer sent. So we are just going to say buffer sent, and we're just going to say str len buffer. So this print statement, it's simply going to print out the length of the buffer which was sent, right? And finally we will be waiting for 1 second before going at the start of the loop, right? And then we will be increasing the buffer again by more 100 A's, right? So we're just going to put buffer equals to buffer plus A into 100, right? Alright, so now we finally just put out the except statement. Let's just say print, and once again let's just say fuzzing crashed at byte, and let's just put this over here. Alright, so this statement is similar to this one, so it's basically going to print out the length of the buffer at which our program actually crashed, right? So now finally we just exit out of the program. Okay, so everything looks good. So our fuzzer is actually ready, so we're just going to go over here and let's say python./fuzzer.py. Alright, so if you now go back to our Windows machine, whoops, it's not actually, it's this one, yep. As you can see, the program crashed, and as you can see, we actually overwritten the EIP, and the IP registers over here, it says 41414141. So 41 is basically the hex code for A, right? So we can actually confirm that we overwrite the EIP. So now let's actually find the offset of EIP. So let's just first of all restart the program, and let's just click on run. Alright, let's go back to our Kali machine, and as you can see it says fuzzing crashed at 400 bytes, but we're actually gonna be choosing 300 bytes because that's the exact byte at which FTP server crashed, right? So let's just generate a pattern now. So we're just going to say msf pattern underscore create dash l. So we basically specify the dash l flag, and we specify the byte, the number at which our program actually crashed, right? Now, why we are doing this? So we are simply going to copy this pattern generated, right? And instead of sending the buffer this time, we are simply going to send the pattern. Now, why we are doing this? We are doing this in order to get the exact value of the EIP offset, right? So let's actually copy this, and let's just create a new variable called pattern equals to our pattern, right? And now let's actually send our pattern instead of our buffer, and let's just start the fuzzer again. And once we send it, and if we go back to our Windows machine, we get the we actually see that our program has crashed. Now, in order to get the EIP offset, you simply have to copy this. You simply have to copy the value just beside the EIP register, right? So we're simply going to click on copy to clipboard. Let's go back to our Kali machine, and let's just say msf pattern offset, and we have to specify the dash q flag. And whoops, I guess my clipboard actually missed. I don't know why it didn't work. Let's actually, manually type that. So I'm just going to go back, and the EIP value is 346941133. Alright, let's go back to Kali, and let's just say 346941133. Whoops, I actually didn't spell that correctly. And there we go. As you can see, it says exact match at offset 251. So our EIP offset is 251, right? So we can just copy this, and let's just remove the pattern variable, and let's just say offset is equals to 251, or let's actually just set 251 over here. Alright, so now we completed the first three steps. So we basically identified a vulnerable entry point to the program, and the second step was to crash the program. So we basically fuzzed the particular program, right? And we finally found the value of the EIP offset. So now it's time for actually controlling the EIP. So we have to verify once more that we can actually control the EIP, right? So now instead of sending 100 A's, we are actually sending 251 A's, and 251 is basically the EIP offset, right? Now we're also going to send 4 B's at the end, so that we can actually confirm whether we are overwriting the EIP or not, right? So now I guess everything is correct, and we can just run the script. So let's say python./fuzzer.py. Let's go back to the Windows machine, and as you can see, the EIP register, it says 42424242. Now 42 is basically hex code for B. So if you go back to the script, and if you check, we are sending 4 B's at the end, right? So we can actually confirm that we are controlling the EIP. Alright, so now I'm just going to restart my program, and I'm just going to run it. And now actually it's time that we start searching for bad characters, right? So there's a really good blog out there on Google from where you can actually copy this bad character array and you can just paste it in your script. uh, it should be actually over here. It should be over here. Yep. So you can just copy the bad character array, and this time, after sending B's, we are also going to send the bad character array, right? So let's just go back and let's just run our further. Well, let's go back, and there we go. The program has crashed. Now, in order to identify bad characters, all you have to do is just click on the ESP register, right click on the ESP register, and just click on following dump. So once you click on following dump, just yep, I don't know why. Okay, just a minute, my scroll is not working. Alright, so after 4Bs, we have our bad character array, right? So you can actually use automated tools such as Mona in order to generate a byte array and compare it with your bad character array, and you can just find bad characters in the program, right? But I'll actually go with the manual way of identifying them by simply just clicking right clicking the ESP register and clicking on following dump, and you should see your hex dump over here, right? So now, as you can see, we have 1 2 3 4 5 6 7 8 9, but after 9, you can see that we have 27 over here. And if you just go back to your script and compare this particular bad character array, as you can see, you have 0A after 9, right? And over here it's actually 27, so we can confirm that 0A is indeed a bad character, right? So we can just make a comment over here, bad chars x 0A, and of course x00 is indeed a bad character by default, as x00 is actually a null byte, right? So it's basically going to terminate our shellcode. So now let's remove 0A from here too, and let's just go back to our Windows machine and let's restart this, and let's just go back. Let's run the script once again. So python./fuzzer.py. If we go back, once again the program crashes. We can just right click on the ESP register, follow and dump, and if we go above, as you can see, we have 1 2 3 4 5 6 7 8 9, and after 9 you directly have 0B, right? So after 0B you have 0C, and after 0C, as you can see, we have 27. But actually, if you go back and compare it in our script, uh, after 0C you actually have 0D. So 0D is indeed another bad character, so let's just put 0D over here, x0D. Let's just go back, control C out of this. Let's restart our FTP server. Let's just click on run. Let's go back, and once again the program crashes. So follow the same steps, just right click on ESP register and just click on follow and dump. Alright, so now if you just go above, as you can see, we have 1 2 3 4 5 6 7 8 9, 0B, 0C, and after 0C you directly have 0E. So if you see over here, if you compare with your bad character array, after 0C we directly have 0E. So basically there are no bad characters after this, right? I actually have exploited this program earlier too, and there are just 3 bad characters, which is 00, 0A and 0D. So if you want to check once whether if there are any bad characters in the script, you can just copy this particular array and just go back, and you can just right click over here and just click on search for binary string, and you can just copy paste it over here. So if you click on OK, as you can see, we find the particular hexdem. So we can finally confirm that we have no more bad characters in our script. Well, so let's just go back and let's just restart the FTP server. Alright, so now it's actually time that we find the Jmp Esp pointer, right? So there are various ways of finding Jmp Esp pointer. So what you can do is you can just click on, you can just press Ctrl F on your keyboard, and a window should pop up on your screen saying find command, right? So you can just enter Jmp Esp over here, but as you can see, we have no pointers such like that. So you can just say, if you have the Mona module installed, what you can do is you can just type a command called Mona modules, and this is basically going to list out all the executable modules um, in the program, right? Now, the only binary which we have over here, which is not having any kind of memory protections, is the ftp server.exe, but it also doesn't have any kind of jmp esp pointers. So what we can do is we can just click on view, and we can just click on executable modules, and a window should pop up. And what we are going to do is we are just going to select any one of the DLL over here which has a JMP Esp pointer. So in this case, the shell32.dll has a JMP Esp pointer, so I can just double click on this, and we can just once again press Ctrl plus F and search for JMP Esp. Now as you can see that we have the JMP Esp pointer, so we can just simply copy this, so copy to clipboard. But now, if you noticed, if you just go back to our log data, and if you check the shell32.dll over here, uh, it's actually yep, here. As you can see, it uses all kinds of memory protections, and of course, it is a Windows DLL, right? So it's basically it's a Windows DLL, of course. You can see the path over here. It says C Windows System 32 Shell 32.dll, right? Now, it only doesn't uses the NX compact memory protection, but it actually uses all other memory protections such as ASLR, rebase, safe SH, and so on. Now, uh, when the computer is going to reboot, the memory addresses, the DLL addresses are actually going to change, and all the pointer addresses are also going to change, right? So the JMP ESP pointer which we just found right now, this one, it won't work the time you reboot the computer, right? So if you reboot the computer and if you try to run your exploit script, it won't work, right? Because there is no such address like this. So the addresses are basically going to change, and that's why ASLR is used, right? Let's just copy to clipboard, and if you go back to our Kali Linux machine, I'm just going to remove this, just paste it over here. Okay, I actually forgot my clipboard is messed up, so I'm just going to note the Jmp Esp pointer address. So it's 76A290FD. Let's just go back and let's just say Jmp Esp 76A290FD. Alright, so let's actually declare a variable now called Jmp Esp, and now we are basically going to store the address in the little endian way, right? Because of the 32-bit architecture, right? So we're just going to say let me actually put spaces over here so it's easy for me to read and you guys too. Alright, so let's just say /xfd /x90 /xa2/76. So we are basically putting the address over here in a reversed manner due to little endian way, right? And that is used in 32-bit architecture, right? So now we finally once again create another variable called knob slides. So knob is basically used for shellcode padding, so that our shellcode actually gets space and we can actually execute our shellcode, right? So let's just say x90, and I'm going to assign 32 over here, right? So it's basically going to be 90 into 32. So we actually assign pretty much space for the shellcode to execute, right? So now let's actually generate the shellcode. So let's just say msf venom dash p windows exec, and let's just say cmd equals to calc.exe. First, I always like to test it out by simply popping off calc, right? And if it works, we are going to replace the shellcode with a reverse shell, right? And let's just say exit func equals to thread. So this basically stabilizes our shellcode. It's nothing much, and we're going to say dash f for specifying the format, and we are going to generate it in a C format. And finally, we specify bad characters by specifying the dash b flag. And then we have x00, x0a, x0d. So let's just wait for the shellcode to generate. There we go. So we're just going to copy this particular shellcode, and let's just create another variable called puncode, and let's just add a bracket over here. Alright, so now we are simply going to remove b from here, and we are going to put jmp esp plus knob slides plus pwn code, right? So once again, let's actually go over the code, and let me just explain you once again what exactly is happening, right? So we basically found the bad characters, which are 000a0d, and we again finally found the Jmp Esp Pointer. So we are simply going to jump at this particular address and execute our shellcode, right? So we are basically jumping to the stack and executing our shellcode. And pwn code is a variable which holds our shellcode, and then we have the Jmp Esp value. It's the Jmp Esp pointer address, and then we are using nops for shellcode padding. So we are storing the nop bytes into a variable called nop slides, and we are finally forming our buffer. So let's actually replace this with the payload. Let's replace the buffer name with payload, right? And 251 is basically our EIP offset, and in payload we are storing all of these values, and we are basically sending that to the FTP server, right? So once again, let's actually refactor the code. So it's going to get this indent off, and let's just remove the while true loop, and over here let's actually print out payload sent, and let's okay, yeah, this is completely fine. All right, so let's just go back and let's check whether our FTP server is running. Yep, it's running. I also actually want to set a breakpoint at the Jmp Esp pointer address, so that we can know that our Jmp Esp pointer was actually hit, right? So let's go back. Let's run the script, and as you can see, it says breakpoint at shell32.dll, and we basically have our Jmp Esp pointer over here. So let's just click on run, and as you can see, we finally pop a calculator over here. So we can confirm that this is actually working. So finally, let's actually close this, run this once again, and let me actually make sure that my defender is turned off. So I'm just going to go to Windows Defender settings, manage settings, and turn off real-time protection. And yep, temper protection is okay. Alright, so let's just click on run. Let's go back. Let's generate the shellcode. So just say msf venom dash p windows shell reverse tcp. LOS is equals to my Kali Linux IP address, which is oops, actually ifconfig, and my IP address is 192.168.1.4. Let's specify the L port, which is going to be 4444. Format should be in C. Let's say exit func equals to thread. Let's specify the bad characters, which is x00, x0a, x0d. Alright, so everything looks good. Let's just generate the shellcode and let's just listen for incoming connections on port 4444. Let's copy the shellcode. Let's go back and just replace the shellcode over here. And okay, so everything looks good. Let's just go on and let's just run the fuzzing script. Let me just check if my FTP server is running. Yup, it's running. I don't know why I keep forgetting that, but it's okay. So let's just run this, and as you can see, we have a reverse shell. So yep, we basically exploited the buffer overflow vulnerability in free float FTP server, and we indeed have a reverse shell now. So guys, that's all for today's video. I hope you enjoyed, and I'll be seeing you all in the next video. And in the next video, we are going to exploit an application known as SLmail, right? So it's also vulnerable to buffer overflow. So yeah, I'll see you all guys in the next video. Have a good day. Thank you so much, and bye.